many years has it been that you've worked with the sanitary district?
10? The USGS has been
I
working longer than 10, but I think, no, I think me on Green Lake, I think it's about 10, but the USGS is about almost, well, over 20.
Yeah, I was going to say it might be closer to 30. Dale's an adjunct professor for UW Green Bay, Michigan Tech, University of Toledo. He's also an honorary fellow with the Center for Limnology at UW-Madison. His current research with USGS deals with, as we all know, lake modeling, looking at eutrophication and mixing in lakes. He's dealing with determining, loading of nutrients from watersheds. And also now I notice it says examining effects of climate change, and we're, that's part of what we've been talking about, ice on, ice off on Green Lake, and, a variety of things, not just the nutrients themselves coming in from the watershed, but how this is all cycling in the lake. So Dale's gonna take us through a lot of information. Dale, do you want people to ask questions as we go, or would you prefer they wait till the end?
I guess it depends if they're looking for clarification, probably right away. If it gets into some of these longer ones, it might be better to wait till either. I'm going to do it in 2 sections. And so we could have a break in between those 2 and ask for some questions, just depending on how the time's going.
That's probably a good way to do it. Just to clarify, so we've invited not only the lake management team, but we also have the Green Lake Sanitary District Board of Commissioners, which is why we had to open the meeting. But we also have the Green Lake Association board, or a good number of them, and we welcome you guys, and we're looking forward to having more joint meetings in the future for, for all the work that both organizations are doing. This is a really exciting, a new thing that we're starting. So I think that's great. So with that, I will pass it to you, Dale. Paulie, are you going to turn over the controls to Dale? Okay.
Good morning, Ken.
Morning, Bonnie.
Yes. Excuse me.
Okay, can everybody see my first slide?
Yes.
Sure.
Okay. Now, before I get into this, typically what I do is I really try to describe the last year in detail. This year, I'm only going to really breeze through that really quickly, because there's a study that we've been working on for the past few years, which is really trying to look at things that we can do to the watershed, to the lake, to try to reduce the surface total phosphorus concentrations and reduce this thing that maybe some of you have heard about, it's metalimagnetic hypoxia in Green Lake. Now with this, it's not just a USGS effort, although we have a couple people, Ben does all the sampling. I only rarely get on the lake. Paul Renault helps with some lake studies. And then in some of the different aspects, we have Corey McDonald, who's helped out with some of these things, and Stephanie Prelwitz. And we also had a few people from the universities help out, which is Robert Ladwig from the University of Wisconsin. And then a colleague of mine from for a long time is David Hamilton from Australia. So we've had a crew of people looking at some of these things. So with that, we have been sampling the lake for a long time. The USGS started sampling the lake in 2004. We're continuing it up to the present, but there is studies that go back to 1905. Now with this type of information, we've been collecting huge data sets on the lake, which is great. We can look for trends, we can look for changes, look for unusual years. Here's just an example of the total phosphorus concentration that we're measuring in the west side of the lake. And you can see we've got a lot of data out there. What we typically try to do with that, though, is smooth it down to we can see what's really happening in the lake. With all that data, it's hard to see. So one of the things that we've done is broke it down into annual averages. This is the summer average. And 3 of the things that we look at in detail are the nutrients, the phosphorus concentration in the lake. This is the source of the problem. The algae in the lake, basically how green it is, and then finally how clear the water is. In addition to that, we measure dissolved oxygen, which I'll talk about in a second. But based on those 3 parameters, if we look at the last year, what we see is that phosphorus concentrations were pretty high. Algae was only pretty high, but the clarity was actually pretty low. So that's what 2020 was. Trying to explain why the water clarity dropped as much as it did is pretty difficult, given that the phosphorus was only moderately high and the algae was only moderately high. So this is where, if we really want to get into the specifics of clarity, we're probably going to have to look at the biology a little bit more in detail. Now, with that information, what we try to do is to compare the lake with some of the standards that are out there. For a lake like Green Lake, the standard for the lake is 15 micrograms per liter. That's what the lake, if it goes above that, then it could be listed as impaired for total phosphorus. And with the historical data that we've collected, one of the things I'm going to be talking about is a reference period of 2014 to 18, because that's when this big study started, or was using as a base period. And with those 5 years, what we see is that the concentration on the west end of the lake was about 17, 16.9, east end was about 20.9, and both of those are above that 15. So the lake could be listed as impaired for total phosphorus. Now,
Dale, I'm sorry to interrupt you. Could you, for just a moment, could you explain to the group about sampling east side, west side, and what the DNR requires for reporting and determining the status of the health of the lake?
Sure, I'll get into that in just a little bit, but for now, let's just keep it east and west side. But I'll get to that in just, I got a slide in just about 2, so I don't want to jump ahead to that one. I'll do that. But when we look at this, the base period that we're using is 2014 to 18, which had a lake-wide average of about 18.8, a little higher than a study period that the DNR used. The DNR used a period from 2009 to 2013 and came up with a concentration of 17. And that's mainly because it's looking at this little dip in the few years around 2012 and 13. But anyhow we look at those, the east side and the west side are both above this criteria. The other thing that we found through all of our monitoring is that there's a problem with the dissolved oxygen in the lake. Typically what we see is that up near the top, you might see somewhere between 8 and 10 milligrams per liter of total phosphorus. And then at the bottom of the lake, we see it drop down to often 0 at the very bottom, and it could even take up a big part of that bottom water. But in Green Lake, what we see is that there's the bulge about 12 meters down, and we see that gradually progress as the summer goes on. So we start to look at this as we go from, in this one it shows April, June, July, August, and September, and we see it getting worse and worse as the summer goes on. And for that, the DNR really wants to keep that, and other people, there's other reasons, but we want to keep that above 5 milligrams per liter. Okay? If it's less than 5, it could also be listed as impaired. So with all that information, the lake was actually listed as impaired several years ago. If you could see this, good eyes, but Green Lake is listed down there for being impaired for low dissolved oxygen. So those second of those 2 things is what the lake was listed for. And it was saying that the cause, if you further can read into there, it says the pollutant was driven by high total phosphorus concentrations. So the lake was officially listed as impaired. Now, with that, there was also a big TMDL that was done, a total maximum daily load, a study looking at trying to improve the water quality of the Upper Fox Wolf River area, primarily looking at the Winnebago chain of lakes, Winnebago pool. And with that, in that study, it showed several lakes that could be listed as impaired for total phosphorus. If you go down there, Green Lake is listed on there, and it says, again, what I just said, the goal was to have 15 micrograms per liter. And when that study was done, that's where they came up with that 17 I was describing earlier. But the 17 was really looking at a lake-wide average. And based on that, the study in that TMDL looked at what it would take to take that lake-wide average from 17 and bring it down to 15. And that study showed that 2 things. First of all, it showed that the current loading to the lake was about 11,000 pounds. But you had to reduce that to get it to 15. That study showed you had to bring it down to about 9,300 pounds, or a reduction of about 18%. So that's what that study was showing. But we have this huge amount of data that's available for the lake. When the study was ongoing, we were already started this study looking at the lake in more detail to look for how to improve the dissolved oxygen. But we're also looking at trying to estimate that load better. We have, as part of the study, and even before that, we added more sites to the watershed. We weren't just looking at the one site that was available for their study. We ended up having 4 sites in the watershed, so we can come up with a much better load into the lake. So the first part of this talk, what I really want to do is talk about what kind of refinements and reductions in the phosphorus loading from the watershed are needed to reduce the phosphorus concentrations in the lake. If we go back, if we go back, the DNR had stated this, but since we have all this data that were specific to the lake, what we wanted to do is, first of all, see if that load is right and see if that is really what it takes to bring down the lake down to that 15. So the goals of this specific part of the study were, first of all, see, is that reduction appropriate that the DNR came up with? How much of a load reduction is really needed to bring it down to 15 micrograms per liter? To do this, what we want to do is go back and look at all the water quality in the lake. We've been collecting data for a long time. It's never really been published other than in data. We want to get that out there so that it's available and in a publication where everybody can see it and compare with other things. Next, we want to quantify the phosphorus budget. We've been doing this in a halfway manner for a long time, but as part of this study, we want to really look at it in detail, not just a few gauges around it, but estimate the total loading to the lake. And finally, determine what kind of load reductions do we need to get that down to 15. The DNR said we needed about an 18% reduction, but with all this increased data, do we stay with that? So we've got all the data that we've been collecting around the lake. I described that. We've got not only 2 sites in the lake that we're measuring, the east and west ends of the lake. Typically the east may be a little bit worse water quality than the west side. Looking at the loading to the lake, you've got these black triangles. All of those have gauges in the lake where we can estimate how much phosphorus is coming into it. So with all that data, what we came up with is, first of all, a base period. You need something to compare with to see what it's going to take to bring it down to that 15. So on the east side of the lake, for the years that we considered our base period, which was 2014 to 2018, the east side had a concentration of 0.02, which is 20 micrograms per liter. The west side was 16, and the lake average was 19. So it's a little bit higher than when that TMDL was done. But one of the things that has changed since that study was done was that we wanted to look at what it would take to remove it. And the DNR decided that instead of looking at a lake-wide average or the west side of the lake, what we want to do is to look at the worst monitoring location, and that's the east side. And so what we want to do here is to try to find out what it would take to improve the entire lake, which would be mainly the, for our worst site would be the east side. So now instead of looking at what the DNR did originally, which was to look at the whole lake, we're going to look at what it takes to improve the east side of the lake, which will ultimately improve the west side also. So when we go in here, that's the number we're starting off with. The DNR started off with 17, we're starting off with 20. And we want to see what it takes to bring it down to 15. So the approach that we're using here is an approach similar to what the DNR used, which is using a Canfield-Bachmann model, which relates total phosphorus concentrations to primarily the load coming into the lake. That's the L. There's a few other things like the mean depth and the residence time, but the main thing that we're relating total phosphorus concentration to is the loading that's coming into the lake. And we want to find out what it takes to bring it down to 15 micrograms per liter. So if you look at that equation, the first thing we have to do is get a good estimated load to the lake. Now, in the earlier study, the DNR used a SWAP model for the entire basin. We've got the data. We want to go in there, see what that load is to the lake. So to do that, what we did is I constructed a complete phosphorus budget where the P input to the lake is equal to what we have monitored. Now we got 4 monitored sites around the lake, estimating, I'll show you later, almost 90% of the load coming into the lake. There's a little bit that we don't have monitored, but there was a study done on the lake by Paul Bumgard from the UW Green Bay, and we can use that information to estimate these few little unmonitored areas. We want to estimate how much is coming in from precipitation. I did a study on Delavan Lake. People may know about this, 50, 60 kilometers to the south, closer to Milwaukee, sort of down in that area, where we estimate how much is coming in from precipitation. This is one of the few studies that have been done to estimate how much is coming in from precipitation. And so I wanted to describe that in this study. Septic systems, Lisa helped me with this to try to figure out how many septic systems are draining into the lake or potentially draining into the lake. And then we pretty much use the literature values on how much comes per septic system. Everybody knows there's a lot of geese on this lake. There was a study that was done several years ago to estimate how much that might put into the lake, so we included that. And finally, I also estimated internal loading. These models typically do not include internal loading, but I wanted to include that here just to see, because that gives you an idea, if we reduce the external loading, how long it may take to get the lake to respond. And I'll describe that in a little more detail later. So with all of that, we're measuring it at 4 tributaries. We got,
Dale,
yep,
I think someone's in the waiting room.
Paulette, can you let them in?
That's what I'm trying to do.
Okay.
But
all
I
right.
think because you have the host, you have to do it.
Oh, all right. I'm going to try to do this. This is hard because of the way my screen shares, but 1 second.
Is that correct, Stephanie?
Wow.
I'm not sure if Dale needs to do it or you do, but, or if you're able to, I'm just not able to see that on my end.
Oh, now I'm really in trouble. Oh, I can see it. Okay, I can invite somebody. All right.
Thanks, Polly. Sorry about that.
Okay.
No, I'm just,
Let's
because
see if
I'm
I
not
can get
seeing
that.
them.
Okay, I admitted them. Okay, I'm back.
Hello,
All right.
thank you.
Okay, they're in. They're on the
okay.
phone.
Okay, Paulette, let me know. Now I know how to do that. So I can do that pretty
Okay,
quickly.
so you're back at it.
Okay, so anyhow, we've got the 4.
Thank you.
You bet. So we got the 4 tributaries to the lake that we're monitoring.
Thank you.
We didn't monitor them for all the years, but we're able to use that to extrapolate to all 5 years. So with that, we got that part of it monitored very well. And what we do is, people may have seen these silver boxes around. We have a couple of the, we have one on Silver Creek and also one over at the Southwest Inlet. And at each one of those sites, we have water, it collects water samples, and we take those samples, send them into the lab, and from that we can estimate how much of nutrients phosphorus is getting to the lake. As I mentioned, there was a study by Paul Baumgard who estimated loads from all over in the watershed, and we can use those relationships to estimate the total load from the unmonitored areas. With that, we came up with a total load to the lake. Now this is for that period from 2014 to 2018. This is the load from all external sources. So Silver Creek represents about 40% of the loading to the lake. The Southwest Inlet represents about 24%, Hill 11, White 4. So you can see, based on those 4 monitoring sites, we have a much better estimate of the load, of measured load, than the DNR could have ever had when they did that earlier study. That's because we added some of these sites, we've been monitoring in detail. Plus we also have atmosphere, septic systems, and waterfowl. So with that, we come up with the total estimate to the lake, which is quite a bit higher than what was used in the Upper Fox TMDL. And there's a little bit, our period is a little bit wetter, but it was mainly caused by just having really good local measured data. We also estimated the internal load. Now, in some lakes, this internal load is what comes out of the bottom sediments and gets into the lake that year. Like on Winnebago, anything that comes out of the bottom sediments gets up into the upper water and it produces algae during that summer. In the case for Green Lake, it's very different. It gets into that cold bottom water and it's stored there until about November when the lake completely turns over. It's released into the epilimnion when the water is really cold and not much happens. And that holds all the way to the next year. So this could be a reason what drives the productivity every year, because some of that stuff coming up from the bottom, it's sort of that legacy phosphorus that comes in the springtime at the same, or it comes up in the fall, but stays all the way through to the following summer. Okay, so we really have 2 phosphorus budgets. We have the external, which is about 9,000 kilograms per year, and then the internal, which is quite high, which is about 44%, but that's really hard to control. Usually when you reduce phosphorus loading, the theory is that if you reduce the external, the internal will drop also. So now that we have the phosphorus loading, the next step was to go in and see if the model works. So when we take their model and look to see what the model would calculate versus what's measured, we come up with pretty close points. One is the lower dot is for the west side of the lake. The upper dot is from the east side of the lake. But overall, it fits into
Bill?
the cluster. Yep.
Sorry, I have one more person coming in.
All right. Okay, they should be here again.
Thank you.
You bet. So if we look at those two lakes, they actually fit right in the curve with everybody else, which gives us a little credibility that the model should work when we start reducing the load. The next thing to do is to come up with a response curve. So on the bottom axis, what I have is a percent change in external phosphorus loading. Basically everything, all the loading to the lake except for atmospheric loading and waterfall. And what we want to do then is to try to come up with and see how that concentration should change as we change the external loading to the lake. So the first part is plot the point where that we have that. In this case, you can see the model did pretty well. If we included internal loading, this is just a test, we'd see that we would have gotten a number much higher than this. So in generalities, you don't use that in this model, and we won't be using it either. The next thing is to run that model using a whole changes in external loading to see what the response curve looks like. And this is what we would get. So with a 50% change in phosphorus loading to the lake, we can see a predicted phosphorus concentration in the lake. Okay. Now, after we have that, the next thing to do is to calibrate it, adjust it back to the little differences on that curve that I showed you before. So what we want to do then is to drop it down to the measured concentration. It just basically shifting that whole curve down a little bit. Now what we want to do is to look at what would be the load reduction to get the lake to get down to 15. Now, if we use the west side of the lake, that's what this curve is for, what we'd find out is, so I bring it down to see where it crosses that 15, and it says that we need about a 17% reduction in loading to get the west side of the lake down. But we really wanted the east side, so I'll go through this again. All right, so that was actually pretty close to what the DNR had suggested. Now, if we look at the west or the east side of the lake, what we do is come up with a different curve. That's this green one up on top. It starts at a different concentration because the east side's a little bit higher. And so what we want to do is to try to figure out what it's going to get that green curve down to 15 micrograms per liter. And once we get over there, we see where it crosses the red line, and we see it actually takes about a 46% reduction in loading to get it down. Okay. Oops. So now what we can do is to take that as a 46%, but we can translate that right into the total phosphorus load, and I'll talk about that in a second. So the other thing we can do with this model is not only see what it takes to bring it down to the 15 micrograms per liter, we can look at it and see what the lake was probably like before we had agriculture in the basin and what we had urban in the basin. And that's by looking at how much typically comes off forested areas. And by doing that, we get these two dots over here at reference. And it says that probably before we had agricultural and urban in the basin, the concentration was somewhere between 7 and 11 micrograms per liter. So it was lower than the criteria and quite a bit lower than where we are today. If we want to get that lake Green Lake to be classified as oligotrophic, which means 12 micrograms per liter, we need between a 48 and 67% reduction in loading.
Yeah, I'm on a Zoom call right now.
Oh, all right. So not only can we look at total phosphorus
Yeah,
concentrations.
can I do it about 11 o'clock my time? Okay, thanks, bye.
Bob, could you please mute yourself?
Sorry, I thought I was.
So with models similar to this, we can also look to see what those phosphorus load reductions would do to things like chlorophyll depth or chlorophyll concentrations and Secchi depth by doing the same approach using a little bit different models. And what we get from those is it says that if we reduce the load by that 46%, we can get the chlorophyll to drop somewhere between 4 and about 5 micrograms per liter. And we get the Secchi depth to improve. But the models are really noisy for Secchi depth. If we reduce that loading, because there's zebra mussels, because there's other things in there, it's hard to say exactly what's happening, but the water clarity should improve a little bit. So Now that is what we have today. There is internal loading to the lake. It represents about 44% of the total load. What is the effects of the internal loading? Really what it does is it's going to delay things a little bit. If we get that, the load reduction that we're talking about, 46%, internal loading will reduce it. But based on some studies that I've been looking at, it appears that it might change pretty quickly. I don't want to go into that right now. I can talk about it later. But I think that if we reduce the external loading, internal loading should respond pretty quickly. Okay, so conclusions on part one. Right now, the Green Lake does exceed the phosphorus criterion by about 2 to 6 micrograms per liter, depending on where you are in the lake. To reduce that, we need to reduce the load by about 46%, getting it from about 80 kilograms down to about 54.80. Now, this is a little bit higher than in the TMDL. The TMDL said we want to get it down to 42.35, but that started off with a higher concentration, a higher loading to the lake, and it also did not look at the worst side of the lake. So there's a couple of reasons why we need a little bit a higher load reduction. We need a higher percent, but since we started off at a higher amount, we don't have to get down as low as what was in the TMDL. We need to reduce controllable inputs by about 48 to 67 for the lake to be considered oligotrophic. And finally, Green Lake was historically a oligotrophic lake, and I estimated somewhere between 7 and 11 micrograms per liter. So that's the first part of the study, and I think I'll open it up for a few questions and see if anybody's got anything right now. But what we're trying to do here was that since we had all the data that we've been collecting on the lake, we wanted to really refine what was in the TMDL. The TMDL was done on a lot of lakes all at the same time, and it didn't really look at trying to improve the east side of the lake like we're doing here. So is there any questions?
Yes, Dale, this is Ken Bates.
Yep.
My question is, you collected so much data. Is it possible for us to get a copy of that data or to get like a comparison of an annual report?
I am producing a report right now, and I'll have all this information in it. It's actually gone out. Number of the people on the call have seen it already, mostly as in a reviewing state, but I'm hoping to have this as a full-blown publication by the end of this, well, somewhere by the end of this year, hopefully digitally before that. But
The reason
all
I'm
the data,
the reason I'm asking is because you're throwing a lot of data and a lot of figures at us to try to digest. So to be able to look at it,
oh, I completely
offline.
agree, Ken. I completely agree.
Thanks.
And all the data, technically, they've been out there forever. As we collect them, they go into our database, and they are available, although they're not available like I put them all together here. But all the information will be coming out fairly shortly.
Dale, Bob
Further-
Walker here. I apologize for everyone for not having mute on earlier. I was wondering about the drop in clarity that you've seen over the past, 1 or 2 years. Could that be more dissolved organic carbon coming in that might affect the water quality and the Secchi depth?
It could be. I don't want to. We don't have the data to support it or dispute it either way. Personally, I don't think that's what it is, but it could be. We had some higher load years. We'll see. If that was the case, right now the load this year has been extremely low, and with that, you would think that it would improve. So we'll see this year probably. But dissolved organic carbon is not something we typically measure coming into lake. It's pretty expensive.
I have a second question about the internal loading.
Yep.
And I've asked this before, and I wonder if you've thought about it more. Would that internal loading be increased if we have fewer days with ice on over the winter?
That's a little bit hard to say. Really what it determines that is when it stratifies. Like this year, ice out went up pretty early, but it's been cool and windy after that. It really determines when it sets up and when it breaks down. With climate change, that whole period should lengthen and that number will probably increase.
I just wanted to point out for everybody that's new to the State of the Lake meeting, we talk about all the different monitoring that's going on, and Dale showed, the different monitoring locations. Up until 2021, the last few years, the sanitary district was able to fund the monitoring of the lake and the tributaries up to almost $100,000 annually. But, due to some budgetary constraints, we've needed to dial that back to about 70,000, at least in 2021 and potentially for a few years moving forward. So I think it's important that our partners understand the financial commitment that the district has put into the monitoring for the last few years, and to know that that's going to change a little bit in the coming years. So I just wanted to let you know that. And as far as like Dale was saying, the information that's out there from the USGS, that's one thing that we've struggled with a little bit. It's difficult, but for those of us who are not very computer savvy, it's difficult to find that information on the USGS website. So we appreciate Dale giving us the information in one document. We do not get an annual report, so we can't provide all of you board members and team members with an annual report of this state. So the State of the Lake address is very critical to our understanding of what's going on. Dale, I did have a question. You mentioned off of Bob's question about the SECI readings. I hear a lot of anecdotal information from longtime residents on the lake talking about, higher winds, more windy days, potentially a product of climate change. What do you think higher winds or continual winds have on the lake as far as continually mixing and maybe impacting water clarity?
That's a good one, Lisa, because I'm actually have a graph that I'm going to show you that in a little while. But you're right. Winds, not only anecdotally, winds have increased and they have become a little bit more variable. And both of those are affecting how much mixing is going on in the lake and possibly the amount of productivity. So the winds really have changed a little bit based on the data that we have, and I'm going to use to run a model in a minute. They have increased and they do affect, have an effect on things. So
they do also limit the number of ice days, because I think what we saw this year, we would have seen ice earlier, but it was never calm enough for it to finally finish setting up.
Right. I didn't look at the wind at that time, but you're right. It does affect, it can have an effect on that. The other thing, just to follow up on what you said, Lisa, we have had 4 main tributaries being monitored in the lake. We have cut that down to 2, but we took the 2 main ones. And now that we have the relationship, we should be able to still extrapolate to the other ones. So now that we have those, we still should be able to continue with those. But in terms of what we can present and what we'll have to show, the thing is to look at these key reference sites and see if those are changing. Rather than trying to look at whether the total loading to the lake is changing, let's look at those key reference sites.
I think too, it was a blessing that we were able to afford to do that, the most amount of monitoring in the wettest years, the highest loading years. I think that's at least the best information to have in this.
Right. Yep.
Dale, I wanted to ask you too, so, and correct me if I'm wrong. So we were talking about a 46% reduction to get the water quality down to what, the TMDL requires. So if you were basing the numbers roughly, instead of off of the TMDL numbers, but on the actual monitoring numbers, what do you think that reduction would be to get us down to 15 micrograms per liter?
Right there. We want to get it down to 5,000, about basically 5,500 kilograms.
What percent is that? Is that?
Well, that's 46% of those 5 years.
Yeah.
But that percent really depends on the 5 years I'm looking at, right? So really the way to look at this is not, I know in going to the watershed, we have to get that load reduced by a certain percent, and that's usually what they look at. So we have to bring it down about 46%, but that key number is 5480. That's really what we want to have our loading to the lake. And that includes the stuff coming in from, in that one, it includes the geese, it includes the atmospheric deposition, and all the tributaries.
Dale, just as a point of clarification, I know you use different years for different points in time. As I look at the numbers that are presented up there, that appears to be a loading or a reduction of about 39%, not 46.
Yeah, That's because if you look at that 46, it's actually talking about controllable external phosphorus sources. So the people in the watershed, if you're looking at the farmers out there and they do this action, they've got to bring down their part by 46% because we can't do anything about atmospheric. And unless somebody wants to chase the geese around, we're not going to reduce that. So the 39% is total, 46% is the external controllable sources. So that's going out the farming areas, the part that we can reduce, they have to reduce it by 46%. So it's not a straight number because some of the things we can't do anything about.
So the reduction in loading presented, the 8980 is the controllable or the?
No, that's total. Reduce the total loading from 8980 to 5480, which you said is 39%. The controllable, that's actually, I'll have that in the report too, but that's the part that we have to reduce by 46%. I'm trying to keep both numbers out there because the watershed people, they say, what percent do we have to reduce? That's the number that they have to reduce because we're not going to do anything about the atmosphere. Okay.
Dale, why would the internal load drop if the external load drops?
Two things. Well, okay. All right, I'll try to answer this really quickly. What happens is there's about 40,000 kilograms of phosphorus in the lake in the springtime. 40,000, you can see that's a big number compared to the 9,000 that's coming in. Then as the summer goes on, that number goes from about 40,000 down to 30,000 because all the stuff that the biology that's using it sinks down to the bottom and it's out of the water column. Then as the bottom goes anoxic, some of that phosphorus starts to come back out and that's there for the next summer. Okay. So what's happening is that internal loading appears to be driven by the productivity up in the upper waters. So if we can reduce that productivity in the upper waters, less will sink down to the bottom. And that means less will come back out. Also, part of that stuff that's down the bottom is lost into the bottom sediment forever. So that the bottom sediment is gradually getting thicker and thicker although it's only a very, very thin amount, that's still a fair bit of phosphorus. So the theory is that as you reduce the external load, you're going to condition that upper sediment so that it doesn't release as much. We've got a couple studies that sort of agree with that. The big modeling study I did on Winnebago suggests that, and also some real monitoring data that we have on Delavan Lake suggests that we can bring that internal loading down about the same way.
But for clarification, the point of reaching that equilibrium, there's going to be a time delay to reach that equilibrium, if I'm correct. And we don't know whether we don't know what that is. Is that correct, Dale?
That's correct. Yep. It doesn't look like it's, at least based on the early, the way I'm looking at this, it doesn't look like it's hundreds of years. Like Winnebago, it could take a really long time to get rid of that extra 44%. This one seems to be quicker. How much quicker? I think we have to do a little bit more studies to look at that and see how is that phosphorus bound in the bottom sediment.
Dale, we've been doing a lot of BMPs in the watershed, and we obviously meaning the lake management planning team. What can we say about Green Lake's phosphorus concentration? Sharon, do you mind to mute yourself? Thanks. Okay, so what can we say about Green Lake's phosphorus concentration based on the time frame you showed in that graph? Is Green Lake's phosphorus concentration increasing? Is it decreasing? Or is it just bouncing around normal variation?
For the most part, it's bouncing around natural variation, I think.
But how do we know? I mean, you said you think, but how do we know that?
Take my word for it. I don't want to go away that far back. Statistically, there's no trend in the data. When we look at the last number of years, it's going up and down. I'm not sure how you can actually say something with a direct answer.
Have we ever had in-lake totals this high before, in successive years in the history of the lake that, you would think?
These are the concentrations in the top right here. So if you look at it, if I had to, doing all my analysis, that kind of thing, it appears that the lake was a little worse in 2002, although those weren't data that the USGS collected. So I don't want to say yes or no with that. Since 2004, when we started collecting the data, it looks to be, this top graph, that the phosphorus concentration seems to be fairly steady. And all I can do is go with the data we have. If we go back prior to that, we look at some of the data that the DNR collected. That's these green, red dots here. It looks like it got worse up to about 2004-ish, somewhere in here, when we switched who was doing the monitoring. But since 2004, it seems to be pretty steady. We do have some dry years coming in here, although because there's that huge mass, I'm saying that the loading only represents about 25% of what's coming into it on an annual basis, or what's in there. So it's going to take a while for this lake to respond. Some lakes, the loading coming in is equal to almost what's in the lake. This one says that it takes 4 years to basically cycle through how much phosphorus that's there. But based on the numbers that we have, it seems to be pretty steady. Now there's reasons to believe that the loading to the lake has decreased, and the lake should gradually, come to this new equilibrium. And I'll show you that, or will I show you that? Probably not. But what we have coming in from Silver Creek, the main tributary to the lake, that has dropped tremendously. That has dropped tremendously with the Ripon reducing the amount coming out through their effluent. So that part has dropped a lot. Okay.
So a follow-up question, but first a comment. I would think that, this is a pretty critical question. Are the best management practices making an impact on Green Lake's phosphorus loading? So an editorial comment that I think, we need something more than taking word for it. We actually need actual statistical analysis to say what's happening in the trends. But then a similar question is what can we say about external loading trends? This is a similar question to the phosphorus concentration, but different. Is Green Lake's external loading increasing, decreasing, or bouncing around normal variation?
That we can address. Because we have monitoring sites on those, and we're seeing that. The loading from Silver Creek has dropped tremendously. We have the data that goes back a long time, and we can say it's dropped. I don't have a graph right now to show you that, but it's dropped by about, I think, pushing 50%. I can't remember. It's a big number that Silver Creek has dropped. What has happened at?
I was gonna say, I'm sorry to interrupt, but with Silver Creek, how much of that external, that loading in is from as you said, the treatment plant, but also when the Sunnyside Marsh flipped, and instead of being a source of phosphorus itself from its sediment and so forth, it actually became a sink. So how much was the Ripon wastewater treatment plant? How much was the flipping of the marsh? But how much was the BMP work in the watershed? I think, Stephanie, that's kind of what you're going for, right?
Now with that, I can say that if you take what happened at Ripon and looked at our loading, that's about half of it. If you assume it's a direct conduit of point sources from Ripon to the lake, that explains about half of it. The other half is a combination of BMPs and flipping the marsh. There is a study going on by the university trying to tease that apart a little bit. Right now, Sarah Fuller wrote a paper on this, or did her thesis on it, and we're doing a follow-up study that we're trying to get published right now that's trying to tease that apart a little bit, and we're using that same numbers, trying to just look at that one, but it's not that easy to separate what happened in the marsh with what happened in the, I think we can take the point sources out, but it's not that easy to look at what changed in the marsh with the BMPs in the watershed.
But the benefit of, this is Jerry Speck, the benefit of the corrections and changes at the treatment facility in Ripon, we should be able to pinpoint that, right, from before and after?
Yep, I have all those numbers. We've got that. I don't have I could pull up a different PowerPoint and show you that, but we have that. I've showed you that in past years. We know that reduction. That is a big part of what I'm trying to add to that paper that Sarah's leading on. But it explains about half of the drop in the loading from Silver Creek can be explained by the Ripon sewage treatment plant.
Okay.
I'll tell you what, let's go on from this, and then we can just see what other questions you have, because this is the phosphorus concentration in the surface water. Now what I would like to do is to talk about the other problem, what the lake was officially listed for in the first place, which is these low phosphorus concentrate or low dissolved oxygen concentrations right about in the thermocline area. Okay, so what we want to do, this is what got the lake listed as impaired for low dissolved oxygen. And what we want to do in this part of the study was to figure out what it would take to remove the lake from being impaired for metalimnetic dissolved oxygen problems. We had a discussion with the DNR again, and we decided that since this is a fairly rare kind of thing that occurs, we had to look at this in a little more detail. And based on that discussion with the DNR, we decided that, or they decided that we only want this to occur 1 in 5 years, or 1 in 5 years. I'm sorry, 1 in 4 years, 25% of the time. We don't want it to occur any more than that, okay? And we really would like it so that it doesn't, now this isn't in there, but we really would like to keep it above 2 all the time, because that's really a threshold for a lot of the biology. So that was my own thing, was trying to look at it, want to keep it above 5. So it only drops down there once in 4, and I'd really like to see it never drop below 2 milligrams per liter. Okay. So what does it take to cause that, to prevent them? What we want to do is evaluate, has this gotten worse over time? We want to determine what are the causes of it. If we want to reduce something, we really need to know what's driving it. And finally, try to determine what kind of, what can be done to prevent these from occurring. And I'll show you later, it's really going to come down to, again, reducing the phosphorus input to the lake. So first of all, has it changed through time? What Stephanie, myself, Dick Lathrop, what we try to do is to get all the available dissolved oxygen concentrations that were collected in the lake. They're most consistently collected in mid to late August. And so what I've done is I've taken all those and plotted them up through time. The upper part actually goes back to 1905. If you look at it, in a lot of the years there was a bump there. You know, it dropped down, but it was nowhere near as bad. The worst we ever saw back then was about 6. It probably got worse if I would have collected it, if they had it collected later in September, but it looks like it was about 6. Then in the mid 70s, it started to get worse. 90s, it was really bad, 2004. Now we're sort of hovering around that. Now to try to look at how that has changed through time, what I'm going to do is just take that worst spot on that depth off, okay? And plot that through time, and this is what we get. So back around the 1900s, it was somewhere around 6 to 8. And now in recent years, it's dropping somewhere between all the way down to 0 up to about 5. And if we did that, it appears that, you know, we're pretty steady, maybe dropped a little bit between the 1900 to about 1970. After the mid 1970s, it seems to have come into a new condition. That's what we see in the middle of the lake. If we look way down at the bottom, 60, 65 meters, it looks like things have gotten a little bit worse down there, but not terribly. You know, it looks like it's gotten a little bit worse down there too. So we know that the metalimnetic oxygen minimum has gotten worse in Green Lake. This is August. It probably would be a little worse. The whole thing would be shifted down a little bit if I looked at September, because that's that length of stratification lasting longer. So there's a lot of causes, potential causes of this metalimnetic oxygen depletion. It could be outside sources. It could be the rivers coming in with low dissolved oxygen and going to an equal density and just occurring right there. So that's one possibility. Basically, everything else is in lake. It could be the sediment oxygen. The sediment just uses oxygen at that depth. Or it could be the water column. It could be the phytoplankton being produced and then dying. They use up oxygen when they're dying and so forth, so they're respiring. Or it could be the zooplankton who are eating the phytoplankton and then they're just using up oxygen. So what we try to do is to look at each one of these. The first thing I did was something that Lisa was talking about, was just simply looking at the years and seeing how things have changed. And so what I've done is we have 24 years that I have got this metalimnetic oxygen minimum. And for each one of those years, I could look at the meteorology. I could look at the hydrology, which is basically the flow, the loads, the water quality in the lake, and also certain features in the lake, the physical features like the temperature at that metalimnetic minimum, thermocline depth, the water temperature around there. So what I did is just simply correlate it with things, just see what correlates with what. Also in here, there is the second column, the first column describes how it's related to the metalimnetic oxygen minimum. The second one is year, so it says whether there's a trend in it. So if we look at all the data, what we see then is that the metalimnetic oxygen minimum is most highly correlated with the amount of chlorophyll in the lake during that year. That's the number one factor. The second one is water temperature. So on warm years, it gets a little worse than in cooler years. Higher chlorophyll, lower metalimnetic oxygen minimums. So what it really comes down to, based on the simple correlation, is that the lower metalimnetic DO concentrations occur in years with high chlorophyll, warmer water temperatures, high spring and summer precipitation, and windier conditions, and also poor water clarity. So it gives us an idea what's causing this. The other thing we could do is by looking at this, each of these parameters with year, we can see what the trends are in some of these things. And what we see is that there is a trend towards more precipitation, although hopefully we're done with that trend, we'll see. Windier conditions, that's what Lisa was talking about, and we have seen windier conditions, especially in June, but it's pretty much all summer, June through August, but we do see that in other months also. And we do see that the Secchi depths have gotten overall better through time. Chlorophyll has gotten higher through time. So anyhow, we can look at all that information and see what is sort of correlated with what. The next thing we want to do is to go back to that chart and try to eliminate process one at a time. And the first thing we did is we took our boat. This is a little bit more than what Ben typically uses, but it's a boat. We have it in the office. Behind that, we have this sled. On there, we have a whole bunch of instruments on it. And what we do is we drag that. Here's where we're going up and down through the water column, through the lake, and we can describe what's happening in the lake. Now what we did is we did that in August of 2 years, and this is what we got. It's gonna look like a lot, but the top is showing the density or the temperature, and this yellow trace is how we drove this thing from the Southwest Inlet at Highway K all the way over to the where Silver Creek enters the lake. And here's the yellow trace is showing where we drove that thing. I'm just basically playing on a computer inside the boat with a toggle switch, raising and lowering this thing as we're going through the lake. And what we see is we've got temperature or density, chlorophyll, backscatter, dissolved organic matter, and dissolved oxygen. And what we see is that layer of dissolved oxygen right there, and I've got a little dashed line to show you there. And what we see is it's pretty much spread everywhere through the lake. So we don't, based on this, we really don't think it's caused by water coming into the lake. We think it's being produced everywhere in the lake uniformly. Now what I'll do is I'm gonna chop out this little box here, average all the data together, and this is what we get. So this is a slice through the lake. We see the temperature or density here. See a really rapid change at the thermocline coming down. We see chlorophyll up in the epilimnion and then drops down pretty uniformly. We see this dissolved organic matter peaking right about at the same depth as this low dissolved oxygen. And so this is the kind of information we get with this really detailed data. So what does this tell me? Well, this is what I think it says. About at that thermocline, when the stratification sets up, we have a lot of algae throughout the lake, but that algae at that depth, because of the density, is sort of stuck there. It starts to decompose, and what it's going to do is as it's decomposing, it's using up oxygen. In addition to that, we have oxygen up on the top, which some of that dies, settles down, and it starts to decompose when it gets out of the light zone. This is where it's below where most of the light is. So now we got algae dying from what was there at springtime, which is a big part of this. Also what potentially could fall during the summer, early summer. And both of those, as they die, decompose, they use up oxygen, and I think that's what's driving this. Okay, that's just one looking at the data and how I interpret it. Now, the other way that we really want to look at this was to develop a full-blown hydrodynamic water quality model for the lake. The model that I chose was the general lake model coupled with the aquatic ecodynamics program. It's called GLMAED. And the idea here was to, first of all, calibrate the model, show that it works for the lake. And now I'm going to try to simulate dissolved oxygen, but I'm going to simulate nutrients, algae, all kinds of other things. Then we use the model to see what the causes are. If I can simulate all these other things, it gives you an idea that the model is simulating reality, and I can try to use the model to help with what the cause is. And then finally, once we know the cause, we can try to alter that cause and see what it would take to reduce that metalimmatic oxygen minimums. So this is the model that I've been setting up. First of all, it's got two parts to it. The first part is the physics, how the water stratifies, how it's moving, mixing, and that kind of thing. And to calibrate that model, we need the shape of the lake, the meteorology, the inflow, lake stage, the outflow from the lake. And we also need Secchi depth to say how light is extinguished in the lake. And what we're going to look at is things like water temperature, ice cover, see if it simulates that very well. So we did that. And here I'm plotting up the real data versus the model data. And hopefully you can't see much of a difference. The model data is in black, the observed data is in gray. And you can see it does a very good job with this. I don't have a plot to show you, but take my word for it. It also simulated ice cover very well. So we think we got the physics down pretty well. After we have the physics, the next part is to try to get all the chemistry and biology to work right. And so to do that, I'm really calibrating from the 2013 to 18 period, 1 year longer than that base period. So I have a sort of a startup year. To do that, this gets into some of the things that we've been collecting routinely, like nutrients. This is phosphorus on the top, nitrogen on the bottom. But we also added things to the stream loading as part of this study. We measured that dissolved organic carbon that Bob was talking about. We measured some of these other things so that we could get ideas. We don't have great data for that, but at least we could control what we're putting into the model. We also measured a little bit of biology, which we don't typically measure. We measured stuff with the phytoplankton into the lake. That's the types of algae that are out there. And we found that for the most part, it's really driven by blue-green algae, which was really surprising to me. At least late summer, that's this teal color out here. But there's 3 dominant species of phytoplankton that I was trying to produce, diatoms in the springtime, and then it goes into a combination of green algae and blue-green algae. Okay. We also measured the zooplankton to get an idea of what was out there. That wasn't really that important in the lake right now, but it could be if it could actually explain some of this variability that we were asking before with the difference in clarity. So once we have all that, again, we need all the loading to the lake. Everything I talked about before, now we had available to us, and we could feed that into it. So we have the total loading to the lake from all those tributaries, all these sources, atmospheric deposition coming in. Now we take all that information and try to make sure that the model is working. Now we're not only looking at water temperature and ice cover, we're looking at all kinds of chemistry, the nitrogen, the phosphorus, the plankton. Are we getting those plankton groups that I talked about? And most importantly, does it simulate the dissolved oxygen in the lake? So what I'll try to do is convince you that we're doing that. So to add credibility, like I was saying, we're not just simulating dissolved oxygen, we're simulating a whole bunch of other things. We're trying to simulate water level, the amount of mixing, ice cover, nutrient concentrations, how they change throughout the season. Phytoplankton, are we getting the types of species that we want? Are things settling like you would, theoretically they would, and what we're sort of seeing with our cross sections, and finally dissolved oxygen. So when I simulate that, here's the temperature. It still works very well through that time period. It gets the timing of stratification really well, which could be used. One of the things I'll talk about later is that I have a proposal out here to take this now and look at the effects of climate change, since we have a model running for the lake. It simulates the water level, which is not surprising because of the way I did this, but it does just to show you that the water balance is right in the lake. This is a change in the water level through time. It simulates that very well. Then we're looking at things. Now this is a little bit complicated. What I have is depth from the top of the lake. That's at 74, which is the top of the lake, down to the bottom through time. And so what I'm showing here is 2 years. I'm showing it In that upper left-hand corner is temperature. You can see the warm water appearing somewhere basically in May through September. That's when that warm water is up there. Then you see the lake cool down and it starts up again the second year. This blue band and the second one across under dissolved oxygen, that blue band is what we're trying to get rid of. That's that low dissolved oxygen in that middle zone. And then we also have oxygen consumed at the bottom. It looks a lot worse than it is, mainly because there isn't that much volume in that really deep water, but the oxygen is worse down at the bottom than it is in the middle of neon. Then we're also simulating things like nitrate, phosphorus, the three different types of phytoplankton, the diatoms, the cryptophytes, which are the combination of greens and other types of algae in the lake, and finally blue-green algae. So that's what we're trying to simulate in the lake. We're also looking at all kinds of other nutrients like the organic carbon, particular organic carbon, particularly organic nitrogen, particular organic phosphorus, dissolved phosphorus, carbon, nitrogen. We're simulating all kinds of different things. So after we have it calibrated, I just showed you 2 years because it's easier to show that, but we actually simulated for a 6-year period. And we see that dissolved oxygen right here in the one in the upper part for the dissolved oxygen. You can see that blue, constant blue band in the middle of neon. That's what we're trying to get rid of. Just to make sure that my model was stable, I actually ran it I took those last 5 years and repeated it again, just to make sure that it wasn't just going off into some unusual condition, running out of nutrients or something. And it seems to work pretty well. Very stable model. When we look at the nutrient concentrations, the solid lines are the model, the dots are the measured data, and you can see it's simulating the phosphorus very well from throughout that, the total and the dissolved. The most important here, honestly, which you wouldn't think is where it drops down to almost zero. That's what we really want to get, because that is showing when the model and reality is running out of nutrients. And that's what we really want to get, and we did that quite well. Also for nitrogen. And when we're looking at that, what this is telling me is that the lake is not just limited by phosphorus, it's also limited by nitrogen. But the only way to really improve things is to drop the phosphorus, because controlling nitrogen is much harder. But right now the lake is limited by phosphorus and nitrogen. Okay. We look at dissolved oxygen. How well did it do? The top is the measured data, the bottom is the model, and you can see those two charts are really, really close, which is saying that the model is doing a great job at simulating dissolved oxygen concentrations. What it's showing is 6 years of that little blue band in the middle. That's showing year after year after year that it's reproducing reality. For dissolved oxygen, the most important part, what I've done is I've shown you what the model and reality says at 5 meters, 12 meters, which is about where it's the worst, 40 meters, and the bottom. The solid line is the model. The dots are our measured data, and you can see it does a great job. That's for the west side of the lake. If we look at the east side, that's the number in green. It does just about as good on the east side as the west side. So the lake is really acting as a whole in terms of what this oxygen is doing. So with that, I hope I've convinced you that I've got a model that really simulates reality in Green Lake. It doesn't just simulate dissolved oxygen because I'm forcing it. It's simulating all kinds of things in the lake. So with that, if we really trust the model, now we can go in there and turn off certain processes and try to figure out what really is driving this. So that's what I did here. This is a number of different simulations. One in the upper left is the model that I just showed you. Then I went into it and turned off one process at a time and seen what the effects were. So first of all, I turned off the interflow. I took the stream coming in and said, you can't go down to the thermocline. I changed the temperature so it would float across the surface. And it says, it doesn't have any effect on it, which is what we thought. Then I turned off external loading. Basically took all of the phosphorus load to the lake, dropped it by 95%. If we could do that, we could improve the lake. We could get rid of that problem that we have. Next, I turned off the internal loading. Since it's about 50-50 what I showed you before, turning off internal loading, we could also get rid of this problem with metallomimetic oxygen problems. Either one of those by itself would be sufficient to do it. Then I turned off the sediment consuming oxygen. That didn't have that much of an effect. Had a little bit of effect, but not much. Then I turn off the phytoplankton, which are using all that, the nutrients are coming up. That by itself is bigger than either one of those, but it's the phosphorus that's driving the plankton, which we knew. And finally, I turned off the zooplankton, didn't have much of an effect. So really what this is saying is that the phosphorus loading to the lake is the cause of the dissolved oxygen problem. So with that, what I did is I took a little slice through each one of these charts, right at 12, right between 10 and 20 meters, and looked for the lowest dissolved oxygen concentration on that through that entire 6-year period and plotted that up. And this is what we get. And what we see is that, first of all, we can actually see that sampling in August is not the greatest idea to compare. We probably should have sampled a little bit later because it does get worse. Next we see is that a series of these things don't have much of an effect, which is what I showed you before. If we look at that, we can see that the sediment doesn't have much of an effect. Well, the zooplankton has basically no effect. Interflow has almost no effect. Sediment demand brings it up a little bit. That's this dashed line. No internal loading, that had a big effect. Still had problems 1 year. But if we can really get that external loading down, we can really improve things. So that's really what it was saying. Okay. So just to say that it's not just what's happening at spring overturn. One of the things I wanted to do was to go in there and say, okay, if we took that whole time series and hit it with a big storm event, does what happened during the summer affect things too? Otherwise, it could be all that spring loading, internal loading. So what I did is I hit it with a big storm in March, May, June, and August, and hit a really big storm on it. And what I'm showing on the top is the chlorophyll concentration. It goes up high in early summer, high in early summer. And here's the resulting dissolved oxygen concentration on the bottom. So we have a lot of chlorophyll about early June, late May, early June, then it drops. And following that, the oxygen drops down. If we hit it with those storms, what we see is we can get the chlorophyll to change. With a June storm, we get a second peak over here. With an August, we get a second peak later in the year. If we look at the dissolved oxygen concentrations, the interesting thing here is that only the June storm really caused that metalimagnetic oxygen problem to get worse. If we hit it later in the summer, like an August storm, it's too late. By the time it gets there, the lake is starting to destratify. It might have a little bit of problem later, but it's really only a June storm. And that sort of correlates with the data that I was showing you before. So it's saying that the internal, the external loading is important. The timing is a little bit that comes into play. So what does this tell us about all this? Well, we go through all those. We can say it's not coming in from the outside, or it's not that interflow coming in. We can say the sediment shelves, that sediment oxygen demand is not driving it. We can say the zooplankton aren't really driving it. Really what it is that phytoplankton being produced, the algae being produced and decomposing that's causing the dissolved oxygen problem. So that's the problem in the lake. So the next thing we want to do then is, since we know it's the loading to the lake, we want to take that external loading, just like we did before, and simulate a whole bunch of different conditions. We want to change it through and see what that effects has on it. So here's the existing conditions. What we want to do is to drop the phosphorus loading by a whole series of percents and see what we get. And this is what it is. If we increase the loading to like 75% more than what we get, we can make the oxygen a little bit worse. If we start reducing it, what we see is that 25% makes the oxygen a little bit better, 40% even better, 50%, 57% is where the thing only crosses it once during those 5 years. And that's what we really want to know. But 40% is almost there. So now when we look at that, how many times did that cross that threshold? As we reduce the loading from 75% more than today down to today, and then start reducing it further, we see that it occurs all 5 years at first. Then we get about 25%. We start to make that metalimagnetic oxygen occur only in certain years. Now the 57% chance we can get, or 50% reduction loading, we can only get it to occur 1 in 5 years. And with a little bit more, we can make it so it never occurs. But if we go back to this, what we see is that even with a reduction of 25%, we no longer go below 2 milligrams per liter anytime during the year. which is a critical threshold to a lot of the biology. Okay. So with that, what we do is we can come up and say that we really need to reduce the loading between 40 and 57% from what we had in those years. What would it look like? Well, we get a very different lake. If we could reduce the load by 57%, the lake would still stratify the same, almost the same way, which is up in the upper left-hand corner. Dissolved oxygen would never go down into that blue range, which is what we want. And we can simulate what the chlorophyll would look like and other things. So with that, current conditions, we got this blue band that occurs at the thermocline. We want to get rid of that. With a 57% reduction in loading, we can get rid of that. So it only occurs once in 5 years. But with even a 40%, we can make the lake look very different. So with conclusions then, the metalimnetic oxygen minimum has gotten worse. 1905, it rarely occurred at all. It never went below 5. Now it's a common occurrence. It's primarily driven by in-lake productivity, which is driven by a combination of external and internal loading. All the other sources were really ruled out. Internal variability in the metalimnetic oxygen minimum are also affected by the amount of chlorophyll that's occurring in there, the water temperature, and that length of stratification. If it sets up earlier and it goes on, what's going to happen is that that period of stratification is going to get longer, and that will get worse. So with climate warming, we could be in a worse shape, and we need a bigger load reduction than what I'm suggesting here. To get it to reduce to only 1 in 5 years, we have to reduce that load down from about 8,800 down to about between 4,000 and 5,000 kilograms per year. Pretty consistent with what we wanted for the total phosphorus concentration. Okay. How does that compare? Well, this is what I was just saying. Right now, with this study, to get the DO fixed or improved, we have to get down to about 4,000 to 5,300. To get the phosphorus concentration down on the east side, we needed about 5,400 also. So both studies are saying that this is the kind of external load reduction we need. But there are a few other things to consider as we go along. First of all, the importance of internal loading. A lot of the things I described earlier, we think that as we reduce the external loading, internal loading will also be reduced. You may want to look at that in a little bit more detail to see how that directly affects things. And finally, there are other things that affect the metalimnetic oxygen minimum. Climate change. If the summers last longer, this oxygen is being consumed longer and longer with time. So if we have a longer summer, these metalimnetic oxygen minimums will get worse. Possibly warmer waters. That what I've found is that if the temperature in that area is warmer, oxygen is consumed a little bit faster. And both suggest more reductions may be needed. And finally, in the past, we've primarily looked at August as our indicator month. Maybe that's not the right indicator month because it does continue to get worse after August. We are collecting more data in September now. We're collecting it twice in there, so I think we can get a better handle on that. We just can't compare it back to the 1905, 1906, because that's the only data that we have available to us. So with that, I'll open up for questions, whether it's on oxygen or on phosphorus.
Dale, for your biomass models, where were those samples pulled from?
We measured the algae basically out in the middle of the lake. And they were measured, I think we collected all of our samples from our west side sampling location. But when we did that, we didn't just measure it at the top. We measured it at the sort of in the epilimnion, that warm water, in the thermocline, and then just below the thermocline. And all the samples were sent to a place called Phycotech in Michigan for analysis.
Dale?
Actually, some of those were sent to the state level of hygiene. I'm sorry. The phytoplankton were analyzed by the state level of hygiene.
Dale, I have a question of phytoplankton and maybe phytoplankton loading. is there a potential that loading from the County K Marsh, which is a phytoplankton-rich environment, could be adding phytoplankton to the lake system, ready-made for food for zooplankton, or ready-made to die off and create an oxygen demand, rather than phytoplankton just growing from phosphorus?
Definitely, possibly some of that could be coming in there. How much? I don't think it's that huge, but definitely could be. You know, that could actually be the spark that gets some of these things going. Like right now, the dominant species is blue-green algae. If you give it sort of that seed, that why we're seeing blue-green algae today could be driven by, you know, sort of that source of blue-green algae to get things going. Why one year looks different than the other, I never thought of it that way, but that's a good idea. But we don't measure phytoplankton too often. Maybe that would be something that we could look at.
I think
I don't think in terms of overall biomass it's huge, but I can't really say that because we didn't measure it. But I don't think it's going to be a huge number, but it could be the thing that gets it going to use up the nutrients in the middle of the lake.
it may increase the priority for flipping the County K Marsh if that's a factor.
It would be interesting if we could shut off and just, still have the nutrients, but don't have anything, if we could put a big filter over there, it would be really interesting to see if we could change the type of species that are in the lake. I don't know.
Thank you.
I think that's a good point, Bill. If you think about the fact that the blue-green algae blooms started in the K Marsh last year, I believe in late July, and we had a very late spring. So now this year we have an early spring and things are already setting up with warmer temperatures. The carp have been at the carp barrier for at least a week or so, not in massive numbers, but showing that there's warm water coming out of the marsh already. I wonder how early we may see that marsh bloom this year. And then, like you're saying, pumping, into the lake and providing that food source.
Now, Lisa, I think that's a really interesting thing. Now, we don't typically measure phytoplankton and zooplankton in the lake. I do that in a couple other lakes, Delavan and Green, or Delavan and Geneva. We do measure that. It would be something to look at for those kind of comparisons. They're not cheap. The samples go for about $300 a sample to analyze. But it would be something that it's easy to do. It's just expensive.
Mm-hmm.
When you look at what happened at the other end of the lake at Silver Creek, when we flipped that, it changed things on that end. I think as far as what's coming into the lake, you have a higher flow down there. You have probably less stagnant water. County K Marsh is quite a bit different in that it is a warmer body, I would believe. You just don't have quite the volume of flow coming through it. It's shallow. You got more back bays. It would be setting up for more the blue-green algae at the K Marsh, which is what we're seeing. We didn't see that happen at the other end.
I don't think the temperatures are that much different on the two sides, but definitely the conditions are quite different.
Yeah.
Because we have so many weeds on the one side, I don't think the blue-green on Silver Creek is near as bad.
Right.
Dale, it's clear from your research and analysis that our challenge is to reduce the external load into Green Lake. Do you have any thoughts based on your experience here or perhaps elsewhere in the Midwest as to what measures we as a community could take to accomplish that reduction in external loading, given our watershed?
It really comes back to trying to, agriculture is huge. If you looked at that, the whole, if you look at that whole watershed, there's a lot of yellow out here and that's all agriculture. So what I was trying to do was I was trying to pull up a talk. If I could find one really quick here. Okay, give me 1 sec here. I wanted to show you one other thing, if I can. Shoot, I can't find it. I was trying to show you how things have changed at Silver Creek. Here it is. Okay.
While Dale's looking for that one, if I can interject really quickly, you know, since we have both boards here and I don't see the folks from Fond du Lac County, but Paul Gunderson's with us from Green Lake County. We've been talking for a very long time about ramping up efforts in the watershed. And, you know, one thing that we've noticed here at the district in driving around the watershed, especially after rain events, where we're seeing constant soil coverage, we're seeing significantly reduced sedimentation flowing into the lake. And so Fond du Lac County started a great soil health program, and we were trying to take this watershed wide. I'm just going to put the little rendering up. So this is a brochure that we're working with Fond du Lac County to get finished up. And we're trying to work with Ted Johnson and Chrissy Kozik from the DNR to use our 2 open lake protection grants to potentially help fund this program. And so I think what we're really pushing is to see the watershed be green, you know, see very minimal soil, you know, brown soil, and ramping up the efforts with soft practices as opposed to sediment basins and things like that that we've, you know, really kind of relied on in the past. Is instead of allowing soil to move off of the field or to move to different parts of the field, really trying to lock that soil in place on the field and improve soil health throughout the watershed. So I know here at the district, that's one focus that we've made, is really trying to promote the soil health program and make that one of the biggest outreach programs that we have in the future.
Elisa?
Is that Ted?
Yeah, this is Ted Johnson. I just wanted to make sure you could hear me. I did some research yesterday, and we'll be able to fund those practices, all but one. You know, we're the upgrade of certain equipment.
Yep.
That we couldn't, but everything else should be just fine.
Great. Thanks, Ted. We appreciate that.
Sure.
Okay, Lisa, can you see my screen right now?
Yes.
Okay. So one of the things, you know, was coming in is how have things changed in some of our watersheds? And this is Silver Creek. If we look at the outflow coming in, it stayed fairly steady until about 2015. And then we've had a couple really wet years in a row. And right now that's 2019 on it. If we look at the phosphorus load, we were dropping. It looked really good coming down here. And then all of a sudden it started coming back up a little bit, but that's coming up with the wet years. Now, if we look at that trend in the overall concentration, that's adjusting that load for how much water is coming through it. And what we see is it was up here about 0.25, and now we've dropped by about 50%. So that's really good. And that's what we're looking for. Now, if we take this is that bottom plot. So it's going from 0.25 down to about 0.1, somewhere in there. So that's the improvement. Now, if we take that load of nutrients that's coming out of Ripon from the sewage treatment plant and remove that load or that phosphorus from that curve would look like the one in green. So the difference between the blue curve and the green curve is that potentially what Ripon's wastewater treatment plant improved things. So what you can see is that curve looks like it was really important early on. And now those two curves are coming back closer together, saying that the loading from Ripon, if we reduce it even further, probably is not going to have much of an effect. We've got the load dropped tremendously. That is a really great improvement up there. You know, that's the way that some of these enforcements are doing. But with that, the load has dropped tremendously. And that was about coming down from about 25 down to about 18. That was what that sewage treatment plant could do. Now, the rest of that difference coming from about 18 down to 0.18 down to about 0.1, that's the effects of the BMPs and that changes in the marsh. If you can look at that curve there and say when exactly it occurred, it's hard to say because, you know, when do you think that the marsh flipped over up there?
It was the early 2000s, which was the exact same time
Okay.
as the Ripon wastewater treatment facility upgrades.
Okay, so what we're seeing then is a combination of those two. Exactly, trying to set the flipping from BMPs in the watershed, that's tough to do. Especially when you
easier.
got this huge variability in flow and other things.
But it's easier to do for all the other tributaries that we monitor because we don't have the complicating factors of point source upgrades or flipping estuaries. So Dale, do we have, I mean, it's really helpful to see the reductions in this way. Do we have similar graphs for the other monitored tributaries in the watershed?
Well, first of all, Hill is no longer monitored. It was only monitored for about 3-4 years. So that one's done. That leaves us with the other one. K basically started in about 2013. So we really don't have, the time to see that. But that is one of the things that we do every year is look at that concentration to see how that's affecting things. So we do have that. White Creek does have the biggest potential. It sounds weird, but White Creek is the one that started in 1988 and has a series of periods looking at it. And that's one way to look at it and see how the concentrations have dropped in White Creek.
So to
White
clarify,
Creek-
we don't have that information, but we could, is that right?
No, we do have that information. I just haven't looked at it. So we do have the loads at White Creek. We have all that. I just have never looked at it in detail to see how that has changed through time. So what we do is, if we go back to that earlier graph, we have the flow, which is the top graph. We have the loads in the bottom graph. To get to the concentration, it's just graph 2 divided by graph 1. I just never divided graph 2 by graph 1 to look to see how it's changed for White Creek, but that's definitely possible.
With County Silver Creek coming in, we had the sewage treatment plant of Ripon make a lot of changes. We also put the carp barrier in there because years ago we were catching carp out of there. And once we got that starting to flip there and the carp out of there, that helped a lot also. And if we can get that situation also on the west end, that might help that situation like it did at the east end. But there were two big things then when that flipped over was a lack of the flow coming in from, or lack of the nutrients coming in from Ripon, but also we put the carp barrier in there first of all and got that to flip years ago, probably
Right.
I would say 2005, 2007, around there.
Yeah, and that's what Stephanie was saying. They both happened at the same time. And that's where it's hard to separate. If one would have happened first and then the other one happened second, we'd have been in better shape although it wouldn't be as the big of, you want to do everything, but the more you can get one thing to occur at one point, separate like 5 years and do another thing, it's a little bit easier to determine one effect from the other effect.
Hey, Dale, the last 4 or 5 years have been some of the wettest on record. I mean, you're showing it here, on the slide right there with the discharge for Silver Creek, but and also there's been a large number of very low frequency storm events where we've had, 4 or 5 inches of rain in 24 hours or so. You mentioned that the years of record in your study are a little wetter than the years looked at for the TMDL. Did you look at the precipitation years of the record for the TMDL versus your study, along with the number and timing of these high intensity rain events we've had?
Yep.
A lot of nutrients we get are from these singular, high intensity, low frequency storm events that we get at weird times of the year as well.
Yeah, no, that's something I looked at in detail. What it comes down to is that the precipitation, trying to get my numbers straight here. The precipitation was about 8% higher during that earlier study. 8% lower than that earlier study. And that translated into about a 6% change in flow for those years. And when we look at the loads at Silver Creek, now we're just looking at the end of it, because we're just looking from 2009 to 13. If you look at the lower plot, we're just looking at those last few years. If we look at those, the load actually did not only change like 5%. So Yes, it was a drier period during the first study than our study. But that only had an effect of maybe 8% in precip. That translated, I know you're talking about the intensity and things, but it only changed to a difference of about 6% in flow between those. And we actually monitored, if you look at the loads that were used during the in the TMDL versus this one, it's a difference of about 31%. So it's much higher than those. But it's not terribly surprising. When Cadmus did that work, they only had one of our sites to try to calibrate their model to. And when you're doing one model for the entire system, it is really difficult to get every one of your points to hit exactly. So they were a little bit, their load was a little bit lower than ours. So that's part of the difference. The other thing is that when you looked at that, they're trying to improve a lake from 17 down to 15. And really, based on everything that DNR has out there now, we really want to take it from 20 down to 15. And so there's between those two things, one is that they started off with a lower load than us. And second of all, they started off with a different starting condition. But this is really, when you're doing a great big study like the Upper Fox Wolf TMDL, and then we have all these data that are available to us, there's so little that we had to extrapolate. We had 4 of the main tributaries to the lake monitored during a big part of that period. So I think that our loads were used to calibrate a model, but if you don't even have to calibrate a model and you actually use the loads, you're in better shape. So I think that really pushes for these being a really good look at what we think the conditions are getting into Green Lake.
Our rains and storms are, I'm going to say, very key to what's happening in the lake. We know what happened in 2008 when we had a dynamic, we haven't seen it since then, when we had to shut the lake down for a couple of weeks. We had bridges wash out, we had roads wash out. You know that the stream banks all got washed out on the shores, on the banks of the streams, intermittent streams. Where do you take your samples to know how much it rains? Because it varies a lot around the lake. Where do you get your samples from, or where do you get your information from for rain quantities?
Actually, I have 2 places that I have. One is there's a big database that's done across the entire country that takes all those sites that are measured and tries to extrapolate everywhere in the watershed. And that's what I actually use to that. So the one I used was the center of the lake from this big data set. But there are other ones. It just happens to be that Green Lake is a tough place to estimate the long-term precipitation because those precipitation gauges are coming and going. So there's one at Ripon, there's one at, I can't remember, but I was using 3 of them to try to put it all together. But to try to look at a long-term trend, it's a little bit more difficult because not one gauge ran through the entire period. The only one that I really have is this external data set that I'm using in my modeling study. That's the only consistent one I really have.
So one of our goals.
Okay.
Go ahead. One of our goals would be to continue to monitor the water coming off the fields and try to keep that water on the fields longer, that it soaks in and does what it's supposed to do there. And in turn, when we have storms, we check, okay, is our flow after that storm, it rained 4 inches, what's our flow coming into the lake at that time? How much good have we done to reduce the flow coming into the lake and keep the sediments out?
That's 2 different questions, but one thing I can do is looking at the flows that we have measured. Let's say we took Highway K. If we don't have a rain gauge there, we could put a rain gauge out there very easily and look at that and then start looking at inches of runoff per inches of runoff compared to the inches of precipitation that come down and see if that's changing. Right now we have, and it's not that hard to add precipitation gauges. It's a little bit hard to keep them running all winter long, but once we have them set up in the summertime, they run pretty easily. So we could add that to our sampling. We could put one right on top of the gauge at Highway K. We could also put one either at Spalding Road or downstream, but we could put those out pretty easily. The hard part is that what's coming in Silver Creek is really representing a much bigger watershed. Highway K has a smaller watershed, and it would be easier to look at that one. But it really what it come down to is flow per unit precipitation. That's what you want to see.
Mhm.
And that
Yeah.
would be possible.
Yeah, with your
And you would have-
automated samplers, how often do they take water quality samples in a 24 to 48-hour period?
Right now, in a 24-hour period, probably very, very infrequently. We could, what it comes down to is that every phosphorus concentration costs $25, $27, somewhere in there. And so we collect about 60 to 70 samples per year. And we try to, when we get those big events, I could show you a plot where when we get those big storm events, we're sampling it at the beginning, middle, upper, and lower part of those. So these really big storm events, we're sampling quite well over them. So we really have that tied down pretty good. And it really depends upon site. Some sites we have more than others. And then in addition to those, what we do is we use different things to trigger them. For a while, we were doing that. Charlie Marks was actually going out and sampling and collecting extra samples during the month. I'm not sure if Lisa, if you're doing that, or if we're doing that ourselves right now, but we were doing that. Our ISCO samplers would fire when we had the big runoff events, and then we take base flow samples in between those, so we could get we estimate a concentration every day of the year through that. And the more data we have, the better. But it's really comes down to trying to run things. Obviously, if you have lots of money, you can do anything better. So.
Yeah, we sample every 2 weeks at the County A bridge. So the automated sampler that we have on Silver Creek is actually at the Spalding Hill Bridge before you get to the marsh. But I go out every 2 weeks during the summer and I sample at the bridge so that we can make conclusions of what's actually happening in the marsh and what's coming under the A bridge.
Right. And that's really important because what we can get then is one of them is telling us a lot about the watershed, and the other one is after it gets through that whole marsh and what's getting into the lake, which is buffered. And what we're doing is we don't have a gauge out there at the Highway A bridge anymore, but we've got a really good relationship that we found from before that we're using to estimate the total flow into the lake now. And given that the water, if you watch it, it goes in and out, we thought we got a better estimate by doing that extrapolation than trying to get this little flow going back and forth. But we did have a full year that we could look at, with those comparisons.
Dale, I want to shift for a second to the blue-green algae issue. And I know that's a very sensitive issue. I know there's a lot of other lakes in our area that are in much worse shape than we are. Little Green comes to mind. But correct me if I'm wrong. So we're talking about, especially because of the high rainfall years of the last 3 years, we've seen more nutrient loading. We're seeing generally warmer lake temps. And from what you were showing with the blue-green algae, we think that we have annually just more blue-green algae in the lake each year, or can we make that assumption or not? Because we really only have 1 year of data for the blue-green algae, right?
I don't think we can make that assumption.
Okay.
I don't know with that. The only thing we have to go between those two is chlorophyll concentration, and chlorophyll concentrations have gone up a little bit, but what I try to do is correlate chlorophyll with Secchi, and because we don't have that many chlorophyll concentrations, we got a fair bit, but we got a lot of Secchi depths, and it's not just the USGS collecting it; it's us, Green Lake Association, volunteers, and other places. So we got a lot of Secchi depths out in the lake.
But if we wanted to do blue-green algae sampling, that would be tough to do, wouldn't it? Because blue-green algae can be up and down. I mean, it doesn't persist, right? I mean, you can have a bloom and 2 days later it can be done, or the wind can change and it can be gone. So if we wanted to start trying to determine if we're seeing just overall higher blue-green algae concentrations, is there an easy way to do that?
No. When you're looking at specific species like that, there are meters that we could potentially, we need to put a buoy out there. And then they have certain sensors that some pick up different color bands. And there is one that's designed specifically for blue-green algae that we could potentially put out, but it would mean putting a buoy out in the lake and then with a sensor on it. It's not cheap. The thing that I see is if we could get Todd Miller from Milwaukee interested. He's a professor at Milwaukee. He's the one who monitors Lake Winnebago. He monitors some of these. If we get Todd interested in this, and we're willing to put a buoy out there, we could get some really high frequency stuff, and that would be the person to talk to. Todd's the best at this kind of thing.
And like you said, all of this information would be great to have. And we've had to cut back our spending on monitoring in the last year. And I don't know that that's something that we can do, but I definitely think it's worth discussing. And of course, we'd want to talk to the DNR and get their input as well. So.
Right. I talked to Todd. I'm on a couple of these harmful algal bloom committees on the Great Lakes. Todd's on that also. I'll try to talk to him and just see if he has any, interest in that kind of thing. Because we do have, we have 1 year of data. I only looked at it for general kinds of things. Like I took all the different algae and put it into these different categories. I just put them into blue greens, and the type of blue greens in Green Lake, although they're blue greens, may not be the bad type, the type that are going to cause problems like Little Green Lake has. So it's not just blue greens. Not all blue greens are considered equal.
Harmful.
We did
Equally harmful.
about 2 years ago have a concerted effort to regularly collect grab samples in the County Highway K Marsh for blue-green algae. So one possibility is to just, when we suspect a bloom, collect a sample. And I talked with State Lab of Hygiene, and we could set up a protocol where if blue-green algae is high, then and only then would they do that more expensive kind of microcystin analysis speciation work to determine if it's just kind of harmless blue-green algae versus toxic algae.
But for that 1 year, we do have a bunch of them that give an idea of whether we're seeing those species. I don't have it summarized here, but we do have those data, so we could look at that.
Yeah.
And the person that Stephanie is talking about is probably one of she's with the DNR, and she's and she's really good at this, and she's the one who did the analysis for us. But when it comes down to, I think one of the big questions that's coming out here is that, we produce a lot of kinds of things. The extrapolations that I do, those are a little bit harder to provide. But when we have these key indicator things, like we have the phosphorus, chlorophyll, and Secchi out in the middle, we have the loads coming in. Those we publish every year, and so those are available. It's the kind of stuff where I try to put it all together into a load, because then I do a lot of interpretation in there, and that's why this big report that's coming out will have all the approaches that I've been using. The stuff on Delavan, which is, somebody was saying, well, why did you use something that far away? Well, it turns out the next closest one is nowhere. It's just somebody that pulled out of the air a while ago to come up with a concentration that was sort of pulled out of because NADP, the National Atmospheric Deposition Program, doesn't even measure phosphorus. And so I had done a study up in northern Wisconsin that came up with some of this. Back then, the data I'm using is a little bit old, but what we did is we moved from White Sand Lake up in northern part of the state, and I actually did this on Delavan Lake because we were really interested in how atmospheric was. So that's where the atmospheric conditions come from. So, but those techniques are finally in this report. I'll publish the results so that other people can use those. I wish I would have had those atmospheric depositions when I did the Winnebago modeling. I would have used the same numbers.
Dale, just to confirm, the numbers for percent reduction for hitting the mom presented at the end of the talk, those are from controllable?
Yeah, yep. So the percents are there. The load represents the total load though. And in this report, it'll have both of them.
So the reduction, okay, I thought I had it and now I'm not sure I did.
All the percents represent what we really need the watersheds to reduce their loads by.
So the total loading or the controllable?
Well, the watersheds are the controllable. So all the percents are representing what we really need to get our gauges to show up in as. So by when we put together white or we put together silver and the Southwest Inlet, let's say we add them together, we got to get whatever's coming from them to drop by that percentage that I was saying.
I thought it was the opposite. For the example in the beginning, that was from total and controllable was,
The percents are all based on controllable, which means that that is what the watersheds have got to be reduced by. The loads represent the total loading to the lake, but the percents represent what we have to get the tributaries to drop by.
so is the 8980 the total loading to the lake?
That's correct. But like I said, in this report, I'll have both of those specifically provided.
Okay.
But ultimately, the percents are what we have to get the tributary loading to drop by. Now, Lisa, I know this is quite different than normal. Normally, I don't get into these, but this study we've been working on for, Stephanie, how many years? Quite a few years. And this was the best time to get it all out there. We'll have a fancy publication. Stephanie's taking everything I've talked about, everything that Corey and Mata, his student, we're working on. We're putting all together to have one report that's going to the DNR. This is what I talked about is specifically the parts that the USGS was involved in. But there are other parts that go into coming up with a plan for the lake. And that's the, to summarize our whole report, that's the one that we'll be submitting to the DNR. This one, although everything I talked about, the DNR has reviewed, that's just the USGS report. And it doesn't, I didn't even talk about the stuff that Corey and Mata were working on.
Are there any other questions for Dale?
Dale, thank you very much. I appreciate that. Lots of information there and overwhelming. And I think
Jerry,
we know. Go ahead.
Does this take you back? I remember the meeting we had because we were talking about, well, what can we do? I remember that specific meeting. We were sitting in there. After it, you, me, and Charlie were sitting there talking. And at that point, it was like, well, what can we do? What is a problem? And that's where we were looking at dissolved oxygen. That was sort of led a lot of this into, trying to look at specifically at the metalimnetic oxygen minimum. And so that was, I can remember that the conversation we had, and that led to this whole thing with Stephanie coming in, being a spearhead for trying to get this thing going and moving this whole thing along. We would have probably continued to do the monitoring, but this intense study looking at metalimnetic oxygen minimums really came out of that one of these meetings just like this.
I think looking back from then, it made us aware that, hey, we know we have to keep working with the farmers, the land, and the control the flow coming off the field. And we've been working on that, probably not doing enough, or we have to refine what we're doing, let nature do more of it itself with grass waterways and crops growing versus just trying to put a retention basin. We know that when those strong storm comes, and there's going to be more, some of our retention bases are just blown out completely. And so you're collecting sediment behind them and it's blown out. It's going to have to be some way that we handle the flow more naturally and keep the nutrients where they're supposed to be on the field versus coming into the lake. And what really surprises me is it's not the everyday flows. It's not the 1 or 2 inches of rain. And that varies from end of the lake to the other end of the lake. I've been there. I can drive from one end of the lake and its streams are dry versus the other end, they're flowing and it's dumping sediment into the lake. It varies a lot. And I just think that we just have to, these intermittent streams they're not one of our 8 named streams, they're intermittent. And the one that comes to my mind is the one on Oakwood Avenue that Lisa and I talk about. It's dry. During a rain, it can be dry. And 2 miles away with the discharge of Hill Creek, no, that's not Hill, yeah, Hill Creek. It's putting a plume of mud into the lake, and it's like 2 miles away. And you drive around and you see what's doing that, and you can see the watershed of Hill Creek, and it's a new cornfield. The corn is maybe 6 inches high, not breaking the beads of water coming down yet, and it creates more water and yeah, coming off the field. And you see the other stream that's pretty quiet and nothing flowing just miles away, and you look at that and it's more hay, and it's not your row crops, and you don't see the brown field yet, and just it's different when if you folks can get around during a rain, during a flood, and just see the dynamics of what's happening out there and what's flowing that normally is a very quiet area. That I think is our key area.
Referring to is, sorry, Jerry, what Jerry's referring to is the Emerald Shores Gully. If you've ever been down on Oakwood Avenue and you've seen that huge gully, Jerry and I have seen it when basically we always say there's chocolate milk flowing through it. And last year there happened to be quite a bit of hay and alfalfa in that little kind of sub watershed. And there was very little water flowing through it, and it was mostly clear, which again jumped out to us as, you know, let's really try and make an effort on cover crops and high residue management. And like Jerry's saying, you know, let's protect that soil. There's the correlation of these strong rain events in the spring when we have, you know, crops aren't up, or they're, as Jerry said, very small, and they're not able to help hold that soil. So, but I think everybody on this call knows the benefits of these soil health practices. So,
right, Lisa, the one thing I think when you look at that, one thing to do is step back and don't look at the lake, but look at our monitored loads at the tributaries. And the reason why I say that is that at any time, especially in the springtime, the amount of phosphorus in the lake is about 40,000 kilograms. And for a whole year, you're only putting in 10,000. So what that means is that trying to see the lake respond to that is going to be very hard, but you can see the tributary. And that's ultimately what's driving the long-term picture. So when you're looking at that and you want to see, are you making headway? Really look at these independent gauges. In the long term, you want to look at the lake. Don't get me wrong. But when you got 40,000 and a whole year only puts in 25% of that, you have to be, you know, 1 year may not be the what drives that water quality of that year, but it will control the long-term picture. And that's where I hope this study is going. When you look at it, it does have the effect. Will it drive that individual up and down? Probably not, because you got 40,000 to start with and you're only adding 10. But if you're adding 10 versus 5, it's going to have a completely different trajectory into the future. And that's where I think, you know, we're monitoring. What does it do? You know, it's trying to point the direction, saying that now the only way to get this is to get the watershed to change. And that's what you guys have been working on. I can't tell you how many lake groups I talk to, and I actually have them try to, I don't know how many people tell you that they got their name from, your name from me, but I know like Delavan, I had people that'll probably call here. Lisa, you got ties with Delavan from the past. They're trying to figure out how to get the watershed to change, you know, to do something. And I'm having them trying to look here, because although you think it's slow, this watershed is really ahead of a lot of other watersheds in the state. It really is. And that's good. You know, when we look at it, you know, Stephanie was asking for long-term trends. I don't really see it, but I don't see it getting worse. I don't see it getting worse. And that's a lot of things, that other things are happening. It's holding steady. Maybe, you know, we're seeing positive improvements. We're seeing a positive improvement through Silver Creek. We don't have the data yet, but if we could flip that, maybe we would see that other, you know, percent come through there too. So, you know, it's hard to say that, you know, that things aren't improving, but given climate change, you know, I don't want to say climate change, given the last 3 or 4 years, we're doing quite well. We're holding our own, and that's good. And I don't think it would have held its own if all these actions wouldn't have been taking place.
Any other questions for Dale? Any comments?
Dale, thank you very much.
One thing, Jerry, Lisa, I'm still in my bedroom. The U.S. government doesn't want me to go into work yet, but I'm on my computer all the time and my phone. Anybody has any questions, just give me a call.
Sounds good. Thanks.
People who
Dale.
know I love to talk, so.
And I mean, I want one more comment about these rains, these intermittent hard rains, which really flow the nutrients into the lake. It's not your normal everyday rains, but they don't last long. I've been around when I get out in the car and I can see a ditch full of muddy water. And I drive around to the east end of the lake. I look at the typical ends going into Mitchell's Glen, what's going over there. By the time I come back, I'm going to take a picture of that one I saw right near my house, and the flow is down already. I mean, in a matter of an hour or two, these streams can swell. And once they've dumped their water and their nutrients, they're going back down again. And these aren't the ones that you drive the next day. Well, let's see what's flowing. They're done with doing their damage, and you got to get out there when they're going. And what I'm getting at, that's the ones we have to report, like to land conservation, what farms are doing what, and on that little sub watershed is what I'm saying, very small sub watershed, and get those concentrated on. So that's my
Yeah.
speech.
Yeah, Jerry, the one thing is that we are continuing to monitor the two main tributaries, which have all kinds of little ones coming into them. And we are measuring the flow at every 5 minutes. Every 5 minutes, we monitor the flow. And when it goes up a certain amount, we do measure the concentration. So we are trying to get those little events. If we get a big storm on Christmas Eve, our instruments do pick it up.
Thank you, Dale.
Well, Dale, thank you very much for putting this together and for going through everything so, in so much detail. We do appreciate it. And as Dale said, if anybody has any further questions, we can make sure you get Dale's email. It's actually pretty easy to find online too. So I appreciate everybody being here. I look forward to meeting with the GLA board again in the future. And I thought this was a really great way to share information. A lot of good questions and comments. So thank you all very much for participating. As for my two commissioners that I have left, we still need to close our sanitary district meeting. So I can leave that for Jerry and Bonnie.
Dale, will you please give me host back?
Can I do, let's see, I'm gonna stop sharing first of all. And I think you have to steal it back. I don't think I can give it to you. Unless you know a way I can get, because if I, right now, I think if I get out of here, it'll stop it. I don't want to do that.
Yeah, you are correct. I'm trying to remember how to do
I
it.
think do you have control now?
No, I don't, not yet. So don't leave.
I won't leave. I'm just trying to figure out if there's something I can do. Since you gave it to me, I think you can steal it back.
Yeah, I'm trying to find that spot. Got it. Okay, I got it back. I
Okay.
just had to find the right spot.
All right. And again, if anybody's got
Thank
any
you.
questions, just reach out.
Thank you.
Thank you.
Bonnie, I'll make a motion. We adjourn this meeting.
And I'll second the motion, Jerry.
Motion
Ben
made. and
had to leave because he's in another meeting.
Yep.
All in favor?
Yes.
Aye.
Aye. Okay.
Thanks, everyone. Have a nice day.
Thank you.
Thank you very much, Polly. Thank you, Lisa. Bye-bye.
Thanks.
Are you okay if I end this?
Yep. Go ahead.